we will start with what is called a minimal polynomial. So let t belongs to, or t is a linear operator only. So a linear operator, as I have already told you, that a linear operator is nothing but a linear transformation t from b to b. So t is a linear transformation from b to b, or t is a linear operator on b with dimension of v equals to n. So we are talking about finite dimensional vector space. Then what is the dimension of L of v? So it is clearly n square, because we know that dimension of LVW is m into n. Now here W and V are same, right? So the dimension of LV is n into n, that is n square. Now consider the operators I, t, t square to tn square. They all are linear operator on V. So I is basically the identity operator, that is the identity transformation. I of V equals to V. Then you have t of V is some operator. Then if you have t, then you can also have t square, t cube, and up to tn square. Okay. Now since there are n plus 1 elements and dimension of L of V is n square, what does it imply? It implies that this set is actually LD. If this set is LD, what does it imply? It implies that some A naught I plus A1t plus A2t square up to an square tn square equals 0 for some ai non-zero, where these ai's are in R. Okay. So this is just by the definition of linearly dependent. So what I'm going to do is that we'll just define a polynomial of t, okay, f of t. So let me just write it as capital T, because capital T is the operator. So see, our polynomial is normally we define like f of x equal to x square, x cube, right? So just in place of x, I am taking t, okay, and this t is nothing but a linear operator or a linear transformation. So this t I am defining as alpha naught plus alpha 1t plus alpha 2t square up to alpha n square tn square. And now since the right hand side, so I have just written alpha in place of a, it doesn't make any difference. So now since the RHS is 0, so you have your f of t equals 0. Okay. So it means that this polynomial ft is actually a 0 operator. It is a 0 transformation. So define m of t, that is a set of polynomials. So I'm just these are the set of real polynomials such that my f of t equals 0. So I have taken a collection of all such functions or all such polynomials f of t which are real, such that f of t is actually equals to 0. And now clearly we can see that at least one element is 0, right? So it is not 5, because f of t equals 0. So at least this element we saw that is in empty. So empty is not 5. It is clear. So then there exists some m in Rt such that my mt is generated by m. what I'm saying is that empty is the collection of such functions such that f of t equals to 0. And now I'm saying that okay, if such a collection exists, and since it is non-zero, we just saw, it means there exists some small m such that all the other functions will be a scalar multiple of it or can be generated by this small m, where m satisfies properties, where m satisfies number 1. So the first property is that m should be a member of empty, that is empty of should be 0 operator, okay. The number 2, so this is called the annihilating polynomial. Annihilating polynomial. And then the second property is m is monic. Now, what is a monic polynomial? A monic polynomial is nothing but a polynomial in which the highest degree, the coefficient of the highest degree is 1. Okay? I'll just write for you please. And the coefficient of the highest degree is 1. And then number 3 is if any f belongs to Rt, that if any member is in empty, so to be in empty it has to f of t should be 0, then degree of m should always be less than or equals to degree of f. That is, for any member of empty, degree of m should be always less than or equal to degree of that polynomial. If these three properties are satisfied, then we say that such an m is called the minimal polynomial. Such an m is called the minimal polynomial for t. So this is how we actually define a minimal polynomial. So just a quick lemma I can say. So I'll just give a quick lemma about minimal polynomial. So I'm representing m as minimal polynomial of t, and p I am denoting as the characteristic polynomial. So m I am using for minimal and p I am using for the characteristic polynomial. So the lemma is that the zeros of minimal polynomial and characteristic polynomial are same. Yeah. For characteristic polynomial for the operator t. So we are talking in terms of operator t. For t are same. So what does it imply? It implies that the roots of the minimal polynomial and roots of the characteristic polynomial are same. So you can just prove it quickly. So let lambda be such that tx equals lambda x. So basically lambda is an eigenvalue. Okay. So we know that the roots of the characteristic polynomial are eigenvalues only. So we are taking lambda, that is an eigenvalue, which is the root of the characteristic polynomial, and now we will say that okay, m of lambda is also 0, means lambda is also a root of the minimal polynomial m. So we need to show m of lambda equals 0. Okay. Okay, now note what is m of tx. M of tx is nothing but m of lambda x, and which is 0, and that implies that m of lambda equals 0 as x is non-zero, because x is an eigenvector and eigenvectors cannot be 0. So since m lambda x equals 0, where x is non-zero, so we will have m lambda equals 0. That is to say that lambda is a root of m. This is the first part. Now let me prove the converse also. Conversely, let m of lambda equals 0. That is, I am assuming that lambda is the root of the minimal polynomial. Now I want to show why. Now I will show that it is also a root of the characteristic polynomial. That is, p of lambda also equals 0. So see that m of t I can write as, now see, since lambda is a root of the minimal polynomial m, so I can write m of t as t minus lambda times some q of t. That is, q of t is some other polynomial, okay? And where q of t is non-zero, right? Because if it is 0, then my m of t becomes 0, okay, which I don't want. So since lambda is a root, so I can write the minimal polynomial m of t as t minus lambda times some other polynomial qt. Okay. Now since q of t is non-zero, what does it imply? It implies that there exists some x which is non-zero such that qt of x is also non-zero. This is by the definition, or this is by what we mean that q of t, that a polynomial is non-zero. So let's say, so we will take y is equals to qt of x, which is non-zero. Right. Now m of tx is 0, so I'll just replace this thing by t minus lambda I times qt of x. Okay, and what does it imply? It implies that t minus lambda I qt of x I have taken as y, so I'll write qt of x in place of qt of x. I can write y. So I got t minus lambda I times y equals 0, and this implies that t of y is equals to lambda of y, where y is non-zero. That implies lambda is an eigenvalue, and we know that if lambda is an eigenvalue, then it is a root of the characteristic polynomial, or we can say that p of lambda equals 0. This is what we wanted to show. So this lemma actually tells us that the roots of the characteristic polynomial and the roots of the minimal polynomial are same. Okay. So the lemma tells us that roots of the minimal polynomial m and characteristic polynomial p are same. Now, one thing to note here is that we are not talking about the multiplicity. Okay, we are just saying that okay, if 2 is a root of the characteristic polynomial, then 2 will also be a root of the minimal polynomial. We are not saying the multiplicity, that is, if 2 has occurred 2 times in characteristic polynomial, then it doesn't us see a theorem that if my t belongs to L of B, that is if t is a linear operator, and let's say t is diagonalizable, and lambda 1, lambda 2, lambda k be the distinct eigenvalues, then my m of t is t minus lambda 1, t minus lambda 2, and t minus lambda k. Okay. So this is what does the theorem says. It says that if a linear operator or if t is diagonalizable, then the minimal polynomial is actually can be written as a product of linear factors. So see, here this t minus lambda 1, t minus lambda 2, t minus lambda k, all these are of degree 1. All these are of individual polynomials of degree 1. And degree 1 polynomials we say that are linear. So we have written this our minimal polynomial m of t as a product of linear factors. Okay, so this is the theorem that if t is diagonalizable, then the minimal polynomial is a product of linear factors. So let us see the proof. So what we have to claim. So see, so what do we need to show, or what is our claim? The claim is that m of t equals 0, because if this is 0, then only m can be a minimal polynomial. So to show this, we assume that let beta be a basis of V such that each x in beta is an eigenvector. Now why are we able to write it like this? Because we have seen in our previous classes that if a linear operator t is diagonalizable, then it has a basis consisting of eigenvectors. And now since here in our setup also it is given that t is diagonalizable, it means there exists some basis beta of t such that the basis consists of eigenvectors. So I have just taken one of the elements of that, that is I have taken x, a particular eigenvector. Okay. So what is my mt of x? This I can write as 1 minus or say t minus lambda 1 I, t minus lambda 2 I, up to t minus lambda k I times x. Now see, you can see that actually t minus lambda 1 I and t minus lambda 2 I, or for that matter any I and j, will commute. So what am I trying to say is actually note that t minus lambda ji times t minus lambda ii is same as t minus lambda ii times t minus lambda ji. So in general, you see, linear operators are not commutative. So if let's say if we have two linear operators s and b, so it is not necessary that s composition b will be equal to b composition s, or for that matter you know that matrix multiplication is also not commutative. But these matrices or these special operators t minus lambda I, t minus lambda 1, t minus lambda 2, they can commute. So if they can commute, I can do shifting, right? So I can actually write it in this sense: t minus lambda 1 I, t minus lambda 2 I, up to t minus lambda k I times t minus lambda I times x. So what I have done is that I have just shifted the t minus lambda I term to to the extreme right coordinate. Okay. Now, as x is an eigenvector, so here I think I have not mentioned x is an eigenvector of t corresponding to lambda I. So if there is an eigenvector, there must be an eigenvalue. I have said that eigenvector and eigenvalue, they both come together. We talk about them always together. Okay. So what I have done is that t minus lambda I, as x is an eigenvector corresponding to lambda I. What is the value of t minus lambda I times x? It is 0. So mtx equals 0. So why it is 0? Because see, x is an eigenvector corresponding to lambda I. What does it imply? That tx equals to lambda ix. So I can write that t minus lambda I times x equals 0. Okay. So now since one quantity is 0, so if you multiply 0 operator with anything, it will always give you 0. So this proves our theorem because this is what we wanted to show. Okay, fine. So now just a simple note actually. So this is something I think you already know, but still I just want to emphasize that if A is any matrix with entries as polynomials. Okay, so A is a matrix. A is, let's say A is this matrix 1 plus t square 2t minus t cube. Let us write just 1 here. Let me just write 1 minus t cube. So A is actually a 2 plus 2 matrix, and the entries of this matrix you can see are polynomial. So this I can actually write as this. See, what I can do, I can take all the terms which are free from t. That is, 1 is here. In the second part, there is no free term, so I'll write 0. Then I'll write 1, and then 1. Okay, fine. Then let us see the coefficients of t. There is no coefficient of t here. Here it is 2, it is 0, it is 0, t. Now similarly we can do for t square. For t square coefficient is 1, no coefficient, no coefficient, no coefficient, t square. And for t cube you have 0, 0, minus 1 times t cube. So see, A was a matrix and elements of A were polynomials. Now what I have written I have written A as a linear combination of some matrices. Okay. The matrices are no longer polynomials, right? Matrices are real matrices, and we have multiplied these matrices with some polynomial coefficient. So the point is that given a matrix A whose elements are polynomials, we can actually write them. We can actually write them in this fashion. This is possible. So this is something that we are going to use. So the next theorem that I want to show is the Cayley-Hamilton theorem. So I'll be actually using this. That is why I have just mentioned here. So let me just write it. First, I'll write the Cayley-Hamilton theorem in terms of operators. So I think you know what a Cayley-Hamilton theorem is in terms of matrices. That is, every matrix satisfies its characteristic equation, and we'll prove it. But like, let us just see in terms of linear operator, because as we know that every matrix corresponds to a linear operator or a linear transpose. on a finite dimensional vector space V, okay, and let P be the characteristic polynomial. P be the characteristic polynomial for T. Now, if P is the characteristic polynomial, then what is P of T? P of T is 0. Okay, that is the minimal polynomial divides the characteristic polynomial. So this is statement is for the operator. Okay, this is we are talking in terms of operators. So we'll just see the matrix version and we'll prove the matrix version of it. Show the matrix version. Okay, I should have written it like this. P of T equals 0 and minimal polynomial always divides characteristic polynomial. Yeah. So matrix version, now we'll see that let A is the matrix corresponding to the linear operator T with respect to the basis beta, okay, relative to basis beta of V, then P of A equals 0. So this is the matrix version of the theorem. Okay, so like you can write it in this way, or there is one more statement that is normally used, that every matrix satisfies its characteristic equation. So it is every symmetric matrix actually, because determinant you can find only for the symmetric matrix. So please mention that it is a symmetric matrix. Okay. Yeah. So this is also one statement that some people use, or some in some books it is written like this. So both the statements are equivalent. So we'll prove it. Proof. Now, so prove it actually, we will use a property of the determinants, that we know that B times adjoint of B, A into adjoint of A, or B into adjoint of B. What is this? This is nothing but determinant of B times I. So this is something that we study normally in class 12th or class 11th, in the chapter matrices and determinants. This property is there. So we'll be using this property. Okay. So now, so let us go on with the proof. So let A minus lambda I, that is, I'm taking the characteristic polynomial. What is this? This is some alpha naught times lambda n, alpha 1 times lambda n minus 1, alpha n minus 1 times lambda plus alpha n, right? So what we need to show, that the matrix satisfies its characteristic polynomial. That is, if we replace lambda by n, then also it will satisfy. That is, so this is equals 0. That is, we need to show that lambda naught times an, lambda 1 times an minus 1, up to similarly alpha n times I is the 0 matrix. So here see, in the above equation, here lambda is actually a number, so that is why this 0 is the real number 0. Okay, but now here this a n minus 1 I, these are matrices. So this 0 is the 0 matrix. It is not the 0 real number, but the 0 matrix. this is the thing that we have to show. So now let us prove it. So we have a minus lambda I times adjoint of a minus lambda I. What is this? We just saw it is nothing but a minus lambda I, determinant of this, multiplied by the identity vector. So the RHS is, so a minus lambda I am going to just replace by my original quantity this. So if I replace the RHS a minus lambda I, what do I get? I get alpha naught times lambda n I plus dot dot dot. Similarly we'll have alpha n minus 1 lambda I plus alpha n I. Yeah, so this is what my RHS is going to be. So I just replaced a minus lambda I, that is the characteristic polynomial, and it is multiplied by an I. So let us just give this 1. So this is my right hand side. Okay. Now what is adjoint of a minus lambda I? See, how do we calculate adjoint? So we first take minors and cofactors, and then we take the, we write it in a transpose form. So that is how we calculate the adjoint. So I hope you guys know how do we calculate the adjoint. So it turns out, so whenever we like follow that process, so it is going to be like some matrix B1 times lambda n minus 1 plus B2 times lambda n minus 2, Bn minus 1 times lambda plus Bn. So exactly what these matrices are, we are not bothered about it, but it comes in this form. Okay, so this is what is important, that it will be something like this. What exactly it will be, it depends upon the matrix, where these B1, B2 up to Bn are matrices. Yeah, and they actually, so this is just, and I'll just write it for you guys. So this is actually not important, but still just to make clear, whose entries depend on A. Okay, so this is what my LHS is. So basically my LHS is what? My LHS was a minus lambda I multiplied by adjoint of a minus lambda I, and adjoint of a minus lambda I is this. So my LHS becomes a minus lambda I times this, that is B1 lambda n minus 1, B2 lambda n minus 2 up to my Bn. And now if I just do some algebra, if I multiply it and I rearrange the terms, I get as minus B1 times lambda n plus AB1 minus B2 times lambda n minus 1 plus AB2 minus B3 times lambda n minus 2. So if you just multiply and rearrange the terms, you will get it plus A times Bn minus 1 minus Bn times lambda plus Abn. So this is what my RHS is. Okay. So now since here you see that LHS was equals to RHS, we started where? Yeah, so we started with this quantity. I'll just name it star. Okay. So see, we calculated the right hand side separately. We calculated the left hand side separately of this equation star. Right hand side we have given it as name 1. Left hand side we gave the name 2. So 1 must be equal to 2. So comparing 1 and 2. So since 1 and 2 are equal, so we can compare the coefficients. We get, so just comparing term by term, that is comparing the terms of lambda power n, then lambda n minus 1, and similarly like this. So what do I get? I get alpha naught I equals minus b1, ab1 minus b2 equals alpha 1 I, ab2 minus b3 I got as alpha 2 I, and similarly, you know, we get a times bn minus 1 minus bn equals alpha n minus 1 I, and abn equals alpha n I. So what I'll do is that we got a set of equations, right? We got n plus 1 equations here, you can see, starting from alpha naught I to b1 b2 up to bn. So now what I want to do is that I want to multiply each term by some quantity and then add. So okay, so for just for my understanding, I'll just give them some names. So I'll just give them names. Let's say 1, 2, 3. This is my n. This is n plus 1. Okay. So what I want to do is that I want to multiply 1 by some quantity, 2 by some quantity, 3 by some quantity, and I want to add all this. So multiplying 1 by a power n, 2 by a power n minus 1, and up to this n plus 1 by I, and adding all them. So if we just do this, what we get? If we just do this, so upon again multiplying and adding, we get quantities like a and b1 plus a and b1 minus a n minus 1 b2 plus a n minus 1 b2. So basically everything, every term I'll get as plus minus, and everything will get cancelled out. So dot 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 up to a square bn minus 1 minus abn plus abn, and this is equals to alpha 1 an alpha 2 an minus 1 up to your alpha n I. So you see the terms in the right hand side, they all get cancelled. So they all will get cancelled if you just do the calculations. So they'll will get cancelled, and what we are left with? We are left with alpha 1 n alpha 2 an minus 1 up to alpha n I actually equals 0, and this is what our theorem is. So that is, if I have replaced lambda by a, and still the equation is satisfied. Okay, so my characteristic equation was alpha 1 lambda to the power n, alpha 2 lambda 2 to the power n minus 1, alpha n equals 0, where lambda was eigenvalues. So I have replaced lambda by the matrix A itself. Okay, matrix A and the powers of the matrix A. So a power n minus 1, these all are matrices. So if you plug that in, we still get the 0 matrix, and this is what we have to prove. Okay, so formally there is just some more, I think only 1 or 2 class I'll need just to like finish your classes formally, whatever I had to teach. The second part I am not sure, like, I think Devanjan sir will teach, or I don't know. So the first part, I think 1 or 2 more class will be there maximum. So after those classes, I'll try to give you the solutions of the previous year questions, or whatever I feel questions which are important from this part. So I will give those problems to you. Okay. just mark your attendance.